Good evening.
What's up?
How are you?
Tired.
Sad.
I am sad. I hope you are sad because our course is going to end soon. Very sad about that.
Yeah, because your second test is approaching. It's gonna be definitely
I mean, next semester's gonna be worse, so this is nice.
not next year.
Well, so essentially this is the last official lecture on the new topic in that course, which is Z-transform. If you have any questions about the lecture itself or any administration, please let me know. If you have any questions on the video lectures or any other information that we've got. Thank you. So just a brief reminder about the lecture, the definition of Z-transform.
Yeah, off of the equipment.
So
That's what a student is for.
Sorry, mate.
the results is gonna suck. So one
So if you
person,
have-
I'll do the result.
Do you have any questions? Okay, so you have definition of Z-transform, which is essentially very similar to Laplace transform. Instead of exponent, you have power of Z. And all we will learn about Z-transforms will be basically in parallel to what you have learned already about Laplace transforms. So if you have discrete systems, you're always using Z-transform. If you have a continuous time system, you're using always Laplace transform for the same purpose. It has almost the same properties, very similar in many senses, like convolution property and sheet property. So you will have tables of Z-transforms in the formulae pages, and this is the definition of Z-transform. So instead of exponent of minus st, you have z to the power of minus n. Now, obviously this one is just sequence of numbers, nothing else. So x of n is discrete time signal of some kind, and that signal is just a bunch of numbers, just least vector of numbers, nothing else. It could be infinite vector of numbers or finite vector of numbers. Now, we always need to define where n starts, because if you have sequence of numbers like 1, 2, 3, 4, 5, you need to start from n equals 1 or n equals 0. You need to show where it starts, okay? You always start with n equals 0 in that case, because you start this one is only positive sequences. Now, that n equals to 0 could be at any place. So if you have vector of numbers, which is defining x of n, which is any vector you want, this vector means that all of the other things are zeros, which means that after 4 it will be 0, 0, 0, 0 forever. Okay? Before that it also will be 0. But the question is, where is n equals to 0? So generally, if we just give in general sequence like that, we're assuming that this one is n equals to 0. Or we put in some sort of arrow like that, saying this one is the first one in the sequence, okay? If you want to show that another member is first one, and everything else was like n minus 1, or minus 1, minus 2, minus 3, and that way it's plus 1, plus 2, and so on, then we just put in that arrow anywhere we want. So without that arrow, we cannot know which one is the first one. So this is just list of numbers, right? Default is the first one is 0. Is it clear? So just, if I'm not putting any arrow here, then this one is 0, 1, 2, 3. This is how it goes. Now, when you have some system, and the system is defined by unit pulse response h of n, I just remind you that instead of impulse response for continuous time systems, those systems have h of n, which is discrete number of points. And you have some input x of n, and some output y of n. The convolution rule still holds. So y of n will be x of n convolved with h of n. Now, what is h of n? Like, how do you know what h of n is? You get that system, whatever the system is. You put here delta of n, which is now Kronecker delta, because we cannot put here Dirac delta, which is infinite. Kronecker delta, I remind you that delta of n equals 1 when n equals 0. Otherwise, it's 0. Okay, it's just single 1. Looks like that. We have point here, everything else is just zeros. This one is 1. So this is Kronecker delta. You put in that Kronecker delta instead of x of n, measuring the output. The output is h of n of the system, which is response to that unit delta, unit pulse. Any questions so far? Now, if you remember, computing that kind of convolution is not very trivial. It's like multiplication of polynomials, but still kind of difficult sometimes. So we want some easier ways to compute that output. And this is a way. You convert everything into Z domain. You make Z transform of H. You make Z transform of X. And the Z transform of Y will be just multiplication of XZ by HZ. From that one, you can do inverse Z transform and to get back to Y of t. So from that one to that one, you just inverse Z transform. That's it. This is the way to get to output of any LTI system, this transfer function h of z, to the input which is transformed to x of z. This is the way. Any questions? Okay, so this was a reminder of the Z transform and how we handle Z transforms. Again, very similar to Laplace transforms. This is exactly what we do with Laplace transforms. Just instead of S variable, you have Z variable. But other than that, the principle is the same principle. Okay? The same way we handle in discrete and continuous time systems. So now I want to show you a few examples of questions that are asked on the tests generally, or just interesting in Z domain, and typical kind of tricks that we are using to solve that kind of questions. Okay, so let's start with the first question. The system with unit pulse response will be h of t, h of n. That will be given by n and step function of n. As an input, x of n equals u of n minus u of n minus 1, which is rectangular pulse in time. Two samples, basically. Okay? Find the response. Y of n of that system. Obviously, the system is linear time invariant. We don't use that kind of systems. Now, what you need to do is basically to do that kind of convolution, but in that case, we don't want to use convolution, we want to use Z transform to do the same thing. So the solution will be first transforming everything into Z domain, which means transforming H into Z domain, transforming X into Z domain, multiplying in Z domain, and then making inverse Z transform to get Y of t, Y of n in that case. Okay, this is the solution. So let's transform, and we're just using tables. H of z. Here we're using rule from the table which says n a to the power of n u of n is transformed into AZ to Z minus A to the power of 2. This is what you have in the table. Now, pay attention that this is n times u, and you want to use that thing. In that case, a equals to what? A equals 1, okay, because 1 to the power of n is still 1 for any n. So what you'll get is a equals 1, so it's 1 times z divided by z minus 1 squared. Okay, x of z, and for x of z, it looks like that. So u of n is transformed into z minus 1, and those are from the table, n minus k, u, n minus k, transformed into z 1 minus k divided by z minus a. Something like that. Again, in that case, a equals to 1, and k equals to what? Also 1.
That's because it's the time shift, right? N minus 1. If it was n minus 2, it'd be
Yes.
2.
So this one is 1 and this one is 1, and then you get just u n minus 1. And this one is un. So we need to subtract this one minus this one. So it will be z divided by z minus 1 minus z to the power of 0 is what? 1 divided by z minus 1. And then we get something like that.
Minus
What?
or plus?
It's plus on top, minus on bottom.
Why? Because it's un minus 1.
One should be this one. This is so this obviously cannot be. You say why here is minus, because here is minus,
Right.
and n minus 1 is getting here, and something is wrong in that sign, because it will be z minus 1 divided by z minus 1, which is essentially 1. It cannot be 1, because transform of 1 is delta.
So the input's supposed to be
delta.
plus u.
So something is missing here. So minus 1. Z minus 1. N minus k is 1. U. And I need to check why is that. So this should be minus here. And then it will be 1. Something is wrong in one of the transforms that I wrote. Do you have table to see what the table says on those transforms?
Yeah.
This one and this one,
I think both of those transforms are correct.
both correct.
Yes. It could have just been the initial problem. The minus in the x of n should have been a plus.
In this one?
Yeah. Because then at the end it would have been a plus in the end.
So saying this one was supposed
Yeah,
to
if
be
that was a plus,
let's see.
then
So have n1 Yeah, essentially, if this is minus, this is just delta, right? Because this one is subtracting that one here, so you get delta. So this actually gives the right solution, so it should be plus here, and then to get plus here. Otherwise, it's not that interesting. Then, like, other than that, xn would be just delta of n, which is too simple. Okay, so this is what we get. Now, what is the next step? What is the next step? We need to multiply. So next step, we get into y of z, which is x of z times h of z. And this will be this one multiplied by this one. So it's z times z plus 1 divided by z minus 1 cubed, right? Okay. From that one, we're doing inverse Z transform. And this will be the formula that we are using. N square A N U N is transformed to A Z Z plus A divided by Z minus A cubed. This is what you have in the table. Okay. So what it will be? What is A? A is 1. And then you get something like that. N square U of n. This is y of n. Basically, that's it. So this is the output of that system. Any questions? So again, you can do convolution between those two, and we did something similar to that already in the lecture on convolution. But in that case, it's kind of tricky because basically the h of n is infinite. So it's defined for any n from 0 to infinity. So it will be kind of ramp function. Convolving this ramp function is possible, but, well, a little bit more tricky than anything else. But possible to compute. This is how you solve that with Z transform. Questions? Okay, completely different kind of question. You have causal discrete time system, which is described by difference equation. So this is the system, y of n minus 0.1 n minus 1, which is delayed one, minus 0.5 y n minus 2 equals x n minus 1. Question number 1, to identify transfer function. Question number 2, to determine unit pulse response. Question number 3, stability. To determine stability of the system. Okay, this is what we want to answer. Now, as I said, it's very similar to Laplace transform. What we did with Laplace transform is just to convert left side and right side into a Laplace domain, right? And then finding y divided by x. This is a transfer function. In that case, we're doing the same thing, just doing z transform of z side and z transform of z side, and finding y divided by x, which is transfer function. So let's see what happens. Basically, any delay is z to the power multiplying by z to the minus 1. This is what delay is in z transform. It's just multiplying by z to minus 1. Just to remind you that in Laplace it was just derivative. It's multiplication by s. Right? So here it's multiplication by z to minus 1. This is what we get. So y of n transformed to y of z minus 0.1 from the linearity. This one comes out. Z minus 1 times y of z. Pay attention that all of the z transform is continuous. It's not discrete. Because of that, I'm using also not square brackets, but parentheses, regular parentheses. So all of that is continuous now. Minus 0.5, z to the minus 2, y of z equals z to the minus 1, x of z. Now all I need to do is basically to find what is y divided by x. So I'm taking common y here, here, and there, and x is here. So y of z divided, which is h of z, transfer function, divided by x of z, is basically what I have here multiplied x of z, which is z minus 1. And here it's 1 minus 0.1 inverse z minus 0.5 z to the minus 2. And basically that's it. So I can leave it as is. Sometimes people actually use inverse z in the transfer function, but we use two different kind of representation. So we want polynomial divided by polynomial, right? So it's simplification, and from now on it's just algebra. So how we can make polynomial divided by polynomial? How we simplify that? How we flip it? Yes. This is a question. So I want some function of z here and powers of z, and some function of z here and powers of z, but positive powers, not negative powers. What should we do to simplify it and to make it positive? You need to multiply numerator and denominator by z squared. You just multiply here by z squared and here by z squared. You're not supposed to flip anything or to change anything in the transfer function. This is a transfer function already. This is how it should be. Now you don't just want to get rid of that thing and of that thing and of that thing. So you just multiply by the biggest one, by z squared. So here you'll get z, because this one divided, multiplied by this one, z squared minus 0.1 z minus 0.5. So pay attention that the free coefficient basically was here, the last one, minus 0.5. This is transfer function. Now, what should you do to get from transfer function h of n? What is the relation between transfer function and unit pulse response? Inverse what?
Inverse of the h of z, going back to z. So
You just need to find
the
inverse transform of that thing. Inverse z transform. This is h of n. Okay, this is h of z. H of n is inverse z transform of h of z. So this was A part, B part, h of n is inverse Z transform of H of Z. So you need to do inverse transform of that thing. Now, you don't have something like that in the tables, but you know how to do it for Laplace transform, right? It's partial fraction expansion and all of the other nice stuff in math. Now, unfortunately, we don't have anything like that, like something, some constant divided by Z minus some constant. You don't have in the table something like that. Or plus B, doesn't matter. You don't have anything like that for Z transform. Now what? So you know how to write that thing, right? You can write that thing as A divided by Z minus the first root times Z minus second root, right? Remember that? So you convert that thing into, let's see, so this is H of Z. You can convert it into Z divided by Z minus Z1, Z minus Z2, and Z1 and Z2 are some given roots of the polynomial of second order, quadratic equation basically. Solving quadratic equation, finding roots, putting them here, and this is exactly the same thing like here, right? We know that from Laplace the same thing. So you can write it as A divided by Z minus Z1 plus some B divided by Z minus Z2. And in Laplace, if this would be S, you would just use exponent to convert that thing into exponent and that thing into some other exponent, right? With some coefficient A and B. And you can find those coefficients obviously from comparing here, or from using formula, whatever. But you don't have anything like that for Z. Now what? You don't have that thing in the table. You have that thing in the table.
Divide out Z and multiply it back.
So the idea is basically that you're not doing partial fraction expansion for Z function, but you're doing it for Z function. And then basically you're not doing Z here. You're expanding Z function here. Okay? Now, if you have that kind of expansion, okay, so you wrote H of Z divided by Z, whatever it is, as those two things, you can get back by just writing that H of Z equals AZ divided by Z minus Z1 plus BZ divided by Z minus Z2, right? And those things you have in the table with Z. Trick, okay? It's just kind of tricks that we are using all the time. So automatically you start that expansion for that function and not for the original function. You don't care about the original function because you always will be later multiplying by Z, the partial fraction expansion. Okay, so what is our H of Z divided by Z? It's obviously 1 divided by something. So those numbers unfortunately are not round, so let's see what it is. So it's Z minus 0.759 times Z plus 0.659. Those are the roots. So one root is at 0.75, and one root at minus 0.66. Approximately. Okay? Now we write that as A divided by Z minus 0.759 plus B divided by Z minus, actually plus 0.659. And we need to find A and B. Do you remember the formula, how you find it? First of all, you're taking Z equals to this one, right? So A equals, taking Z equals to this one, and then canceling that part. Just removing, deleting it, and putting that Z here. So it will be 1 divided nothing here, just ignoring it, because you have a division by 0, so ignoring it. You don't need it. You multiply by that thing, and putting here 0.759. So you get 0.759 plus 0.659. And you get, let's see what you get, 0.7052. Because you have a coefficient. B is the same thing as the second pole. So you get 1. Now you're ignoring that part and replacing z with that number. It's negative that number essentially, because z equals negative that number. So it's minus 0.659 minus 0.759. And this will be obviously negative, the same thing. Because this is plus the same thing, this is minus the same thing. 0.7052. Those are the numbers. You can do also common denominator and then to compare coefficients to 1. The same thing. Depends what you like better. You can solve system of 2 equations and then together. In the same technique like what was partial fraction expansion, but for different function, for that function. Now, h of z, in that case, will be z times a, and a will be 0.7052 z divided by z minus 759 minus 0.7052 z divided by z plus 0.659. This is partial fraction expansion. Any questions so far? And now the last step, to convert it back into time domain. H of n will be 0.7052 times 0.759 to the power of n. This is from the table. Minus 0.7052, 0.659 to the power of n. And don't forget to put here u of n, because it starts at 0. It's not defined for negative values. This is h of n. Now, the last one is the simplest one, actually. Stability. Is that system stable?
No.
Why not?
It has a negative root. Or negative
So,
pole.
what we need for stability of discrete time systems? There is difference between stability of real LTI systems, which are discrete case and continuous case. For continuous case, all of the poles should be to the left. For discrete time systems, what it should be? It should be in the unit circle. So the absolute value of the roots should be less than 1. It should be in the unit circle to be stable. Now, do you know why? Any reasoning for that? Why that would be true? So exponent, we know that exponent of negative something will go to 0, so it will converge, right? So this was the reasoning behind like why we need real part of the exponent negative. Because exponent to the negative something multiplied by time, right, which is solution of all of those things, will be decaying to 0. And all of those exponents will be just these exponents of minus t times some constant. If this constant is positive, it goes to 0. Okay? Now, what happens here? Very similar thing. Where those numbers go? They go here, and they are with power n. Okay, so it's some constant, whatever it is, positive or negative, it doesn't matter, times the location of the pole to the power of n, plus or minus the location of the pole to the power of n, and so on, if you have more of those, right? Now, when this thing is converging,
To zeros where the n goes with it.
when this value is smaller than 1.
Yeah.
So if you have value which is smaller than 1, something to the power of n when n goes to infinity, right? It will be smaller and smaller and smaller. If this one is larger than 1, like absolute value of the larger is 1, than 1, where it will go when n goes to infinity? Like power of 2, whatever. 2 squared, 2 cubed, 2 fourth power, fifth power, where it will go? To infinity. The same thing is negative 2. Like negative 2 to the power of 2, it will be 4. Negative 2 to the power of 3, it will be negative something, so it will jump all over the place, oscillate to infinity, basically, right? If this is smaller than 1 in absolute value, then it will converge. Then n goes to infinity. And this is the only case, right? And this is the reason why it should sit inside of the unit circle, between -1 and 1. It's all bounds. So, is that system stable?
Yes.
The system is stable because both of those they are sitting inside of the circle. The system is stable.
And if it was right on 1,
It's
It's stable.
on the boundary between stable and unstable. We define that as unstable. It will oscillate essentially. So you'll have generator.
which one of the tables is they're getting that inverse transform from? That's the z over z minus a.
I'm sorry?
Where you're getting the inverse transfer from those.
From the table. It's like z divided by z minus a.
Okay. So that's like the third one. Just
So this one is linearity, right? So this coefficient could get out from here. I don't care about that coefficient because it multiplies whatever it multiplies. Here too, the same thing.
Okay.
But you need just z divided by z minus constant of some kind,
So-
times u. It will be everything times u here. So it's one of the first, I don't remember the exact line, but
Right.
it's one of the first ones.
So it's the third one. It's just that it would just be an a instead of 1.
You have this one. So this is z to the power when k equals to 0. So k equals to 0.
Okay.
And a equals whatever the pole is.
Alright, what's this one?
So this is number
5.
5 in the table. Any questions? Okay. Let's try something else. Different kind of question where you have xn given as a sequence. And given by the following sequence. You have x of n equals 1, 0, 0, 3, and everything else is 0. Okay, and starts here. No. I would like to start probably let's start with 0. So it starts here. And it continues with zeros, right? So you have as many zeros as you want. You can write that in different way. So it will be 1 for n equals 1, 3 for n equals 1, 2, 3, 4, and 0 otherwise. This is the given vector of numbers. You want to find z transform of that thing. How would you do that if you don't have any formula? It's not a function of n, right? It's just given numbers. How would you solve that kind of equation?
Do the difference equation.
difference equation on what? This is just given x. You don't have any system, it's just z transform is a signal.
You gonna do the column delta one?
But you don't have any system at all. There's not system, there's transform of signal. Just given signal, you want z transform of that input.
Transform it.
You want to transform it, yes. You obviously don't have anything like that in the table.
Use the definition.
What kind of definition?
The Laplace definition.
Nah, Laplace is not a good definition. You have z transform definition, yes. You can use z transform definition. Any other techniques that you can use? But you hope to get the same answer.
Initial value term?
Can you write that thing analytically? Can you write that thing in some sort of formula of n, function of n, which you have like single string,
The summation.
summation of what? Summation of how many deltas? Two deltas. Okay, you can write that as delta at 1 plus delta at 3 shifted by 3. Delta shifted by 1 and delta shifted by 3. But you don't have to. You can use the direct definition. So definition x of z, sigma from 0 to infinity, x of n, z minus n, right? So it's x of 0, z to the minus 0. So let's write it explicitly. It's x of 0, z to the power of 0, plus x of 1, z minus 1, plus x of 2, z minus 2, plus x of 3, z minus 3, and so on. This is what it is. Now, x0 is 0, right? It's given here. Nothing. x1 is what? What is x1? So it equals 1 times z minus 1. What is x2? x2 is 2.
0.
x2 is 0. You don't have any x for n equals 2. It's 0. Falls in that category. How about x3?
0.
Also 0. How about x4?
That's 3.
3 z to the power of minus what?
That's 4.
Okay. So this was easy for us. Now you want to write that as transfer function or as polynomial divided by polynomial. It's not transfer function in that case. You want polynomial divided by polynomial. How can you do that?
You multiply it by do something to it.
You multiply and divide by the same thing. What is that same thing?
The minus 4z. Or z to the 4th.
Z to the 4th. So you're multiplying and dividing by z to the 4th. So on the bottom you have z to the 4th. And on the top you have z to the 4th times z to the minus 1. It will be z cubed plus 3. This is what we want. So this is z transform of that specific sequence. And now comes the most tricky question. Draw pole and zero map of that transfer function. I will give you 5 minutes to draw poles and zeros in that map. Try that.
5 minutes are up.
Those are zeros, those are poles. Draw it. You want
Imaginary.
real, imaginary. You want to put circles where you have zeros and crosses where you have poles. You can discuss it if you want.
What's the value of the cube root three?
There's all at 0.
So, what is the value of what?
Cube root three.
Leave it as is. It's just 1.44.
So that'd be a.
I'm asking more not on specific number, what is the number, but how you get there.
So then we go to 0.
Hmm? What equals to 0?
Numerator and denominator.
So
It's only
the
one.
numerator equals to 0, yes, 4 times.
Right. And then the top.
This part is easy, how about top part?
Well, it can't be. I guess it could be,
So what are the roots of the z cubed plus 3? This is the question.
1 imaginary numbers.
Yes and yes. All kind of.
Have to do that thing, you know, forgot what it was.
Yeah, this is where most students stuck. So this, most students get that part right, you're drawing for
Is it roots
poles.
of unity? Is that the name?
Yeah, roots of unity, yeah. Not in that case, it's not unity, it's roots of 3 in that case,
Right.
but complex roots, yes. Obviously, don't have any more real roots except minus cubic root of 3. Minus goes out of the root, right? Remember that part of the algebra. Anybody has any idea how to get there?
Can I draw a triangle?
Kind of, yeah. Close. Anybody has some more precise answer how to get there? So again, the question is to find, first of all, roots of the denominator. Like what are the roots?
0, 0,
0,
0.
0, 0, 0. You have 4 zeros, and this means that you put in all of those poles, whatever, 4 of them. It's 0. This part is easy. You have 4 real roots, all of them are 0. Now, you need to solve that equation now. How many solutions you will have to that thing? And how many solutions this equation has?
3.
3. Any polynomial of nth order has n solutions, complex solutions, obviously. Some of them complex, some of them real, but in general, complex solutions. You have always 3 solutions here. How you find those solutions? Can you find that thing? Is it real?
Yes.
Yes, this one is real because it's the same thing like taking minus cubic root of 3. It's not like square root of negative number, it's not complex. It's minus 1.44. Is that it? Like you have 3 of them at the same point? Do you have any other roots that satisfies that equation? Or this is the only one and you have multiplicity of 3? Because this is what most students would do, from my experience. They would draw like 3 zeros here somewhere, which is not correct.
Does it go up and down above that?
So obviously you have that one minus 1.44, right?
You just go 120
Which is
degrees.
minus cubic root of 3.
You just go 120
Would
degrees.
that be minus?
You go 120 degrees.
Yes?
Why you go 120 degrees?
Because it's 0 plus.
2/3. Then you make the circle, around the unit circle.
Okay, this is exactly what you need to do. Why do you need to do that? Except that you just have great memory. How to
That's
do
great
that?
memory.
Fine.
What is the reason for that?
Uses the beta term.
Hmm?
The beta term.
There's something with the unit circle.
So you have z cubed plus 3 equals 0, right? So what you have here is z cubed equals minus 3. What is minus 3 in polar coordinates?
3 at negative, 3 at 1.
What I write here,
5.
pi,
Beta.
and
J.
anything else? Is that the only way to get that minus 3 number? This is cyclic, remember, this is circle. It repeats every, what?
2 by.
Every 2 pi. So we can write it as 2 pi n cyclic, right? Because this is exactly the same number, right? For any n. This is true for any n, right? Now, how we make cubic root of that complex number? This is cubic root of the radius. What we do is the exponent.
Divided
Demo
by
over
3. Divided by
theorem. We divide it by 3. This is what it is. Now, pick any 3 consecutive n's, and you'll get 3 different complex numbers. It doesn't matter from which n you start. Let's say you can start 0, 1, 2, or 5, 6, 7, whatever. Pick any. It doesn't matter. It repeats itself every 3 steps. Every 3 n's, it repeats itself. You will get exactly the same roots 3 times. 3 roots, then again the same sequence of the same 3 roots. Now, let's pick 0 here. So pi plus 0 divided by 3, so it's pi divided by 3. What angle is that? Pi divided by 3 in degrees?
120.
No, it's 60.
60.
No, it's 180 divided by 3, which is 60. So you'll have basically the same radius because this is the same value, axis value is the same, but you'll have 60 degrees. So it will sit here. Now pick n equals 1. So it's 3 pi divided by 3, right? Which is just j times pi, right? J times pi is here. This is a number. This is negative 1, basically. Negative 1.44. Negative cubic root. Now, pick this one equals to 2. So it's 4 pi plus pi, which is 5 pi divided by 3. So it's 5 divided by 3 pi. What angle is that?
The 60 minus the 2,
It's
7.
basically adding here the same angle. It will be kind of minus 60.
Right.
So it will be here. So this is how this diagram should look like. Okay? So this is how it works. questions? Okay, let's try different approach. You need to find inverse Z transform of some given transfer function or some signal. And this will be Z squared minus 2 divided by Z cubed plus Z plus 3. You don't have anything close to that in the tables, obviously. And I hope you don't like to solve cubic equations. So, what is the alternative method for finding actual inverse Z transform of that kind of polynomial divided by polynomial?
Long division.
Long division. So this is what you will get. Here you will have something that you divide, and here you will write the answer. Now, so what is the first thing which I need to multiply by that thing to get Z squared?
Z to minus 1.
Z to minus 1. So Z to minus 1 times that thing will get you Z squared plus 1 plus 3Z minus 1. Okay, now subtracting, it will be minus 2 minus 1 is minus negative 3 plus 3Z minus 1. Okay, next one. You want to get this one with this one. Is there anything interesting here? Do you have any Z to the minus 2? So which one is the next one? You want to get from this one to this one. So what we need to multiply is that one.
Z minus 3.
Z to the minus 3. So basically you have 0 times Z to the minus 2, so nothing multiplies Z to the minus 2, minus 3, Z to the minus 3. Right? And then I'm multiplying this one by this one, and getting minus 3Z minus 2 minus 9Z minus 3. And the difference will be
I think you have a sign
3Z to the negative 1 should be minus.
this one,
up one. To the right. That one.
this one.
That should be a minus.
It should be minus 3Z to the minus 1. Okay. So you're doing subtraction here and getting something, whatever it is, and continuing the same way and getting more and more of those terms. Okay, this is the approach. Now, is it convenient approach? Would you like to use that kind of approach or partial fraction expansion approach? So, what is better?
How many terms do we have to get?
Obviously, you have infinite number of terms here, so you will not go too far away.
So do we just go with the same order that
So
was?
here's the question. So pay attention to the question. The question is when you pick that approach and when you pick the partial fraction expansion approach. It depends basically on what you just said. Obviously, you cannot get all of the string here, so you can go far, a few terms more probably, but not too far away, right? Not feasible to write all the infinite number of terms. So when this approach can work and when the other approach will work. when this approach is easier and when the other approach is easier.
This one's not as easy because you have a different, you're trying to subtract a different power. Can you do that?
You can always subtract the powers. You always can do that.
So when you're subtracting right there, you can subtract the 3z to the minus 1 by 3z to the minus 2.
Sure. It will be -3 minus -3 is
Well-
nothing, so it will be minus 3z minus 1 plus 3z minus 2 plus 9z minus 3. That's what you get as the next one.
Oh, okay.
Then you get
Oh, I see, just,
from this one to the next one.
just curves over.
Right.
Yeah, that was down.
So we'll get again. Next one will be, so you need to get to that one, so it's -3 times c to the minus 4, right?
What?
So to get to
Oh,
this
yeah.
one,
Yeah,
this one should be multiplied by z to the minus 4,
yeah,
your next one.
right, okay.
And so on, you can go on with that thing.
Okay.
So this thing is good. Just remember where you can use it. This is simpler than going through all of those system of equations and so on and so on, especially for difficult functions like that. If the question is to find the first terms of the expansion, okay? If I'm asking you, let's say, what is the coefficient of z to the power of -3? Something of that kind, if this is your question, then you can just get it -3 from here, okay? But if I'm asking you to find the entire formula for any term, for any coefficient in the expansion, then probably this is not the way to go. This is not a convenient way for you to solve questions. You need to go through that method, the first one, and not that method. This method is good to find a few first terms in the transform. Okay? And let's see. Something more. Again, something similar to Laplace transforms, but related to initial value and final value of Z transform, which have also very similar theorems. So the question goes like that. You have Z transform of a signal given by x of z, and this is z minus 0.75 divided by z, z minus 1, z plus 0.75. Some complicated signal transform. You want to find x of 0, 0 in time, not in z. Okay, and x when n goes to infinity, which is final value, like when it converges. And for that you have very simple theorems. So x of 0 is limit when z goes to infinity of x of z. It's simple as that. X infinity is limit when z goes, can you guess what? Where it goes?
0.
No. It goes to 1.
Oh, there's a trap.
You
hated that.
Trap. Something like that. Okay, so lots of theorems, you have that in the tables too. So here you just finding that limit, which will be what?
So the second one is the.
So let's start with the first one, it's simpler.
No,
So z goes
just a quick.
to infinity. Where it will go? When z goes to infinity.
To infinity.
Are you sure?
0.
No.
y0.
Because you multiply, but you multiply it on
How
one
do you
end.
know how to compute that limit for z goes to infinity?
0 z cubed. And just,
Because the z cubed is
Consider
in the
the
denominator,
constants.
so it gets much bigger.
You have z cubed, which is much larger than everything else in the same polynomial, and on top you have just z. So the bottom part grows much faster than the top part, right? So basically dividing by larger and larger number when z goes to infinity, which means it has to go to 0. How about this one? So let's write that one. More specifically, z goes to 1, and here we have z minus 1 cancelled with z minus 1, right? And here we have z squared, z plus 0.75, and here z minus 0.75. So basically we just replace z with 1. So it's 1 minus 0.75 divided by 1 squared, 1 plus 0.75. And this thing will be 1/7. 1 divided by 7. This is the final value. So it will converge to the value 1 divided by 7.
in the denominator, should that, you wrote z squared multiplied by z plus 0.75,
Yes.
z minus 1 canceled.
So basically I multiplied that thing here. So it's like multiplying here by z minus 1 divided by z. So this z became together with this z squared, right? And
Yeah.
this canceled with this.
Forgot
So
that.
this is what left. And then this is the final value. So it will change somehow, change, and then converge to the same.